Hello and welcome back. So in this topic, we're going to dive into functions. Now, earlier in the course, we gave a introduction. We gave a definition as to what a function is. So in this section, what we want to do is talk about different types of functions. We want to talk about this thing called the pigeonhole principle and also composition and inverses of functions. But first, we want to continue on from the last topic, which is on recursion. And we want to talk a little bit about recursive algorithms. Now, recursive algorithms is something that we've kind of discussed in that section, but I want to give a solid example just to illustrate what a recursive algorithm is and how we use it in practice. So, an algorithm, as we kind of discussed throughout the course, when you hear the word algorithm, it's really a series of steps to solve a problem, right? So, an algorithm, the series of steps to solve the problem is called recursive if it solves a problem by reducing it to a smaller version of itself. Okay, so it's the characteristic of the way that we're going to do the problem solving that makes it recursive. So if I describe to you, this is how I'm going to solve a particular problem, the nature of how the algorithm is described to you makes it recursive. So for example, I can say, oh, and if you wanted to solve this bigger problem, then first solve the smaller version of the problem and then do this to it to get the bigger version. So that is what we call a recursive solution to a problem. So usually the simplest form of this type of recursive algorithm comes from a recursive definition already, although I should stress that it doesn't have to. So later on in the course, we're actually going to come back to this idea of recursive algorithm. I'm going to show you an example of a recursive algorithm. So stay tuned for that. But for now, let's do one with a recursive definition. So let's do an example like this. Give a recursive algorithm for computing. We'll say f of an is equal to a to the power of n. Okay, so what you're going to be given here is an a and an n. And what we want to find out is what is a to the power of n? We want the value of a to the power of n, where a is an integer and n is a non-negative integer. Okay, so we want to basically calculate the power. All right. So the first thing we should realize is that in terms of a recursive definition, now think back to our previous video when we worked with recursive definitions, what we need is actually a smallest case. Now, this is kind of a weird scenario because we have a function that involves two inputs. It has a as well as n. Now, the short answer is that if we want a recursive definition, only one of these variables has to have a smallest value. Now, if you look at a, if you consider a, is there a smallest value for a? No, it doesn't. What about n? Well, n, yes, it does have a smallest value, that the smallest value is 0. So we can start with n and we can say, given n is the smallest value, what is the value of this function? Now, before we do that, I want to define first what the domain of this function is. Now, it may not be clear to everyone because we have a function that maps something to something. Okay, now the left-hand side of what I write here of this arrow is called the domain, and then the right-hand side is called the codomain. So I'm going to start with the codomain because the codomain says what kind of answers can you get, right? What kind of solutions, what kind of outputs can you get from this function? So the answer here is you can get integers basically, and you can get integers from this function. So when I calculate a to the power of n, they're always going to be integers as an output, right? So what about the domain? So what is the inputs? What is the set of inputs that I'm going to get for this function? Well, you might say integers because a is integers, right? But we also have this n, which is non-negative integers. So how do we specify in our set notation that we have two integers or two things that I'm going to pass in as input for this function? So as an example, maybe I can show you this. If I get something like f of 2, 3, I want the answer 8, right? Whereas if I'm looking for f of negative 2 to the 3, I'm going to get the number negative 8 as an answer. Okay, so you see, we have the output. It's just an integer, right? But how do we specify the input? How do we specify both of these numbers? Now, this notation may look familiar to you because that looks exactly like a tuple. And in fact, that's what we're going to use. We're going to use a tuple in order to specify this. So now, can we be a little bit more specific as to what a domain is, what the domain of this function is? Well, we're going to need an integer followed by a non-negative integer. Now, remember what this cross does. Remember what this cross product does. We get a bunch of tuples in which the first element is an integer and the second element is a non-negative integer. Okay, so we get integer and the second element is a non-negative integer. And I want all such crossings. Now, do you agree that this would be my input? This would be the set of my the inputs for this function. Okay, so once again, what you're looking at here is the notation that says I'm going to pass in as input integer followed by non-negative integer, and I'm going to get as an output some integer. Okay, so again, the codomain is not too important usually because the codomain just says, here's the set of values that I might get as part of an answer. All right, so let's go on to the first part. So the first part says, what is the smallest value? What is the output at the smallest value? So I'm going to say f of a0. So notice that a actually doesn't have a smallest value. I'm just going to substitute an a in here. And then when n is equal to 0, then the answer is 1 because anything to the power of 0 is equal to 1. Now I'm going to include 0 to the power of 0 in there, okay, despite what maybe some of your math teachers have told you. Our definition here is that 0 to the power of 0 is equal to 1. Okay, now the second part is I need to write f of n with respect to f of n minus 1. Now here I'm just going to write f of an is equal to f of an minus 1 and then do something to it. Okay, now again, the strategy that I told you earlier is if I wanted to find the definition of the recursion, then I just write out this represents a to the power of n minus 1. The left-hand side represents a to the n. So if I already know the value of a to the n minus 1, how do I find the value of a to the n? And the answer to that is I multiply it by a. Now, just verify. If I multiply this by a, this is a to the 1, by the way, I need to add the exponents together, right? So a to the power of n minus 1 plus 1, which will give me a to the n. Okay, so I hope you verified. So this is our definition. Okay, this is our recursive definition. But that's not what we're after. We're not after the recursive definition. We're after the recursive algorithm. Okay, so the algorithm says, give me the steps in order to find what the value is. Now, I'm going to draw a very quick diagram here just to indicate how a program or how a programming language would process this, this algorithm. All right, so the first thing we do is we want to find out f of an. That means we're going to need the inputs a and input n. Okay, so let's pretend that we have some inputs a and n. Okay, this would go into the first slot, and what we need to ask ourselves is n equal to 0? So this is the thing that we're asking, is n equal to 0? So typically when we ask a question, it is inside of this diamond. And whenever we ask a question, actually, I should put a question mark here just to indicate that this is in fact a question. Okay, so when we ask this question, we get either a yes or a no answer. Now, if it's no, then I'm going to, so if this is a no, then what I'm going to do is go back and I'm going to make n equal to n minus 1. Okay, so I'm going to, in the process, make n equal to n minus 1, and then I'm going to go back and I'm going to keep going. All right, if it's yes, then I'm basically going to return the number 1. Okay, so I'm going to return the number 1 as an output. All right. So after I have n minus 1, actually, I should probably change this a little bit. I'm going to process this by saying the answer is equal to f of a n minus 1 and then multiplied by a. I'm going to do this process, okay, and which will require me to go back up to the top and replace n with n minus 1. Okay, now I didn't really draw this diagram very well, but in the end, what I want you to verify is that this thing is going to work. Okay, so let's imagine that we're a computer and we're asked to find what is f of 2, 3. Okay, now we have this formula here. We have this flow chart here that we can follow. So the first thing we're going to answer is n equal to 0? No, it's not. So what we're going to do is we are going to solve the problem f of 2, 2, you see n minus 1, and I'm going to multiply this by 2. Okay. Now, at this point, the computer is going to say, okay, I now need to solve a subproblem that is f of 2, 2. So I'm going to put this f of 2, 3, I'm going to put this problem aside, okay, and I'm going to concentrate my focus on solving f of 2, 2. So f of 2, 2 is f of 2, 1 times 2. And now, once again, I'm going to put that aside, and now I'm going to put my focus on solving f of 2, 1. Now, computers are really good at this because it has lots of memory. So it will put this inside its memory and it'll know that once I've solved f of 2, 1, then I can come back to this larger problem. Okay, so this is basically the way that it would process it. So then we would have f of 2, 0 times 2, and then I would put all my focus on solving f of 2, 0. Now, at this point, notice that we went around and around in this chart here. And now, once again, I'm going to ask, is n equal to 0? This time, the answer is yes. So I'm going to give the 1 as an answer. And now f of 2, 1 can be evaluated. So the computer is going to say, okay, I've solved f of 2, 0. So that's gone. I'm left with a number 1. So I know that right before this, I was trying to solve a problem, f of 2, 1. So now I can solve it because f of 2, 1 is now equal to 2. And then right before that, it drags the stuff from the memory and it's going to say, okay, right before that, I was trying to solve f of 2, 2. F of 2, 2 now I know is 4. And then now f of 2, 3, now I know is 8. And you can see that even if I try to solve a larger problem than that, it might go through several more levels of repetition, but we're going to always get the right answer. Right? So ultimately, at this point, the computer is going to report that you were trying to solve f of 2, 3. The answer is 8, but it would have gone through all those steps, all those levels before it found out that the number was actually 8. Okay, so what I've shown you is just an example of probably the simplest form of a recursive algorithm. So if we already know a recursive definition for the algorithm, then really it's just, if the n is equal to 0, then the answer is 1. But otherwise, in every other case, then we have that we're going to solve the function with respect to a smaller function. Okay, so that's always the form that a recursive definition is going to take. Now, as I said before, there are other types of recursive algorithms. So let me point some of them out right now, and then near the end of the course, I will come back and I'll actually talk about another type of recursive algorithm or another example of a recursive algorithm. All right, so the first example is, do you remember when we did the Pascal's triangle? When we did Pascal's triangle, I said one of the nicest applications of Pascal's triangle is that formula, right? That n plus 1 choose r is equal to n choose r plus n choose r minus 1. If you remember that equation, that in itself is recursion, right? So I said before, if I wanted to find like 19 choose 7, I can break that down into 18 choose 7 plus 18 choose 6, right? So that big problem was now broken down into two smaller problems, right? So when I said, yeah, when n was equal to 19, now n is equal to 18. And then from 18, I could break it down into 17 and 16 and so on. And do you remember at the time when we talked about Pascal's triangle, we said there were some base cases, right? Those base cases are the cases where we have n choose 0 and also n choose n. Whenever I encounter either of those, immediately I know that the answer is 1. Okay, so do you see the similarities between recursive algorithms that we're talking about here and Pascal's triangle? Okay, so I hope you can see the similarities because we have the base cases and we also have the recursive cases. Okay, so that's a very nice example right there. There's actually another example that we've done earlier in the course, which was the Euclidean algorithm. Right? Euclidean algorithm is another example of a recursive algorithm. So how is that? So in the now Euclidean algorithm was to solve GCD, right? So what we said was, if I have the GCD of a very large problem, so let's say A and B are very large numbers, then I divide A and B and find the remainder. And so B and the remainder is now a smaller version of that problem. Now, again, if you don't remember how Euclidean algorithm works, go back and take a look at that video, right? But at the time, I said this is a big problem. I've shrunk it down to a smaller problem, and then I shrink it down to an even smaller problem, until if those two numbers, A and B, are divisible by each other, then right away I know that the GCD is the smaller of the two. So that is our base case. Our base case is when the two numbers are divisible, then I know the GCD is the smaller number. Right. So there are lots of examples out there of recursive algorithms. So I invite you, when we talk for the rest of the course, when I share an algorithm with you, try to think, is this a recursive algorithm? Right? Are we solving problems with respect to smaller problems? Okay. So that's a little bit on recursive algorithms. This kind of extends from our very last topic on recursive definitions. But now let's move forward and let's recall our definition on functions. So if you remember our definition from last time, we said a function from set A to set B, and the way that we denoted it was something like this, right? So a function from set A to set B is an assignment of exactly one element, unique element, from B to each element in A. So another way to say that is every input, every A has exactly one B. Every A has exactly one B. And what I said at the time is, if I draw a graph on both sides, if I have a set A, which has a bunch of objects, and a set B, what I'm going to see is that there's going to be one arrow pointing away from A, exactly one arrow pointing away from each one of the objects in A to anything in B. Now, of course, the objects in B can be used multiple times, but what you're going to see on the left-hand side here is every element in A has one and only one arrow pointing away from it. That's our definition of a function. And let me just do a little bit of recap. Um, we'll just call this 8-2 maybe. So we said there are two parts to our definition of a function. The first one is at least one. So every input has at least one output. So for all A, there's at least one B, so that f of A is equal to B. So that's our first part of the definition. The second part of the definition, now this is an and, so both parts have to be true. So for all A, B1 and B2, if f of A is equal to B1 and f of A is equal to B2, then B1 has to equal B2. So let me just put a bracket here. So that means if we have an input that goes to two outputs, those two outputs better be the same. Okay, otherwise, there's going to be a counterexample, and this is not a function. Okay, so so moving on from that, we have to understand that there are some some definitions that go along with our definition of function. So whenever you see something like f1 plus f2 of x, we're really just adding the functions together. When we do f1 dot f2, we're multiplying the functions together. So this is just notation that we're going to use for this course. So just keep that in mind. Now, let's pretend that I give you a function and you analyze it for this definition. So you say, does this definition violate number one or number two? And let's say it doesn't violate. So that means it's a function. So, so could it be a special type of function? Okay, so let's say we've analyzed that f is indeed a function. We can then try to analyze whether it's a special type of function. And I'm going to share with you two special types of function. The first one is called a one-to-one or injective function. Okay, so one-to-one or injective function. And you've probably seen this definition in math, but let's go through it anyways. So a function is one-to-one or injective if and only if. So here's the definition. F of x equals f of y implies that x is equal to y. All right, so what does one-to-one actually mean? Well, in short, it means that every output is has at most one input. Okay, so I'll say that again. Every output has at most one input. That is called a one-to-one function. Okay, every output has at most one input. Every output has at most one input. Now I'm going to underline this just because this is kind of an important point for this definition. So let's talk first about a counterexample because I think we better understand, like it better helps us to understand what does it look like to not be one-to-one. Okay, so let's say we have a function a and we had a bunch of elements in a, and then we had b and we had, let's say, some elements in b, but one in particular has two different inputs. Okay, so let's say we had two different inputs go to the same output in B. Right away, we can say this is not one-to-one. Okay, this is a counterexample to one-to-one. Okay, so here's our counterexample. Okay, so if you ever see two inputs go to the same output, it's not one-to-one. Okay, all right, so let's see if we can officially give a definition of one-to-one. So our definition of one-to-one goes like this. Now, again, the definition is every output has at most one input. So every output goes like this. Okay. And then I'm going to do A1, A2. So I'm going to say that if A1 is equal to B and if A2 is equal to B, so you see A1 and A2 is equal to B, then A1 must equal A2. All right, so let's see if we can read this again. So for every output, for every B, A1 and A2, if A1 goes to B and also A2 goes to B, then A1 must equal A2. So this is the logic that we're going to use to say that every output has at most one input. Every B has at most one A. Now, again, I just want you to see that if there happens to be an A1 and A2 that are different from each other, right? If they're different from each other and they both go to B, then there is our counterexample to one-to-one. Okay, so it's not one-to-one at that point. Could it still be a function? Yes, it most definitely could still be a function, but it's not a one-to-one function. All right, so let's see if we can give a few examples here. So let's pretend that we have a function from integers to integers. And let's say this function goes like this. So this function is xy such that y is equal to x squared. Okay. Now the question is this a one-to-one function? Okay, so you can pause the video and see if you can understand the definition by analyzing this particular function. Is it one-to-one? Now, I think the best way to figure out whether something is one-to-one or not is to first identify is it possible to have an output that has two different inputs? And in this case, I think there is because the domain is integers. Now, I do stress this because um, the domain actually matters. It actually gives you a hint as to whether or not it is one to one or not. So here we can say that f of 1 is equal to 1 and f of negative 1 is equal to 1, but 1 does not equal negative 1. So you see how this is a counterexample to our definition of one to one. Okay, so we can say no, this is not one to one, and it's because of this. Okay, so because f of 1 is equal to 1 and f of negative 1 is equal to 1, but those two inputs are different, then right away we can say this is not a one to one function. And this is typically what we would do if you're confronted with a function and you're asked, is it one to one? Then the first thing you should do is see if there are two inputs that give you the same output. Okay, so if there is, right away, that's a counterexample. All right, so if you take a look at the next point here, whenever we have a function, it could be real numbers, it could be anything else that happens to be strictly increasing or strictly decreasing, then guaranteed it is a one-to-one function. So what we mean by strictly increasing is that the function, if you put it into a graph, it keeps going in one direction. Right? It keeps going up, and strictly decreasing, it means it keeps going down as the numbers increase. So as an example, I can give you this function. So f is equal to xy such that y is equal to x plus 1. Yeah, let's just do this. So is this one to one? Yeah, this is actually strictly increasing. And in fact, another way to argue for this is that there's never going to be an output that has two different inputs going to it, right? There's no such thing in this function. So this is one to one. We'll say because it's strictly increasing. All right. So I want to come back to one of these points that I was making before. Let's say in the earlier example, in this example right here, let's say my domain was instead of integers, let's say it was positive integers. Okay, so we have a domain of positive integers, and this function maps from positive integers to integers. And the relationship is still the same as y is equal to x squared, but this time, is it one to one? And I hope you can see that there is now going to be no such situation where we have one output that is coming from two different inputs. We won't have that situation. So if I simply change the domain to z plus, this function becomes one to one. So that's why we have to be very careful. Now, on a quiz or anything like that, you have to look at what the domain is and also what the codomain is. Those two things together will play a role in determining whether something is one to one or not. So be very careful. Okay, so right now I'm just going to change it back so that we don't confuse ourselves, but I just want to make that point. Okay, so once again, just to wrap this up, one to one means that every output has at most one input, at most one input. All right. There's another type of function called an onto function. Now, an onto function or surjective function, sorry, a function is onto or surjective if and only if for every element b, there is an element a such that f of a is equal to b. So how do we say this in English? Onto means that every output has at least one input. So earlier example, when we were talking about one to one, every output has at most one input. Now we're talking about the fact that every output has at least one input. Now again, let's start with a counter example. What does a counter example of onto function look like? So let's say I have a set A and I have a bunch of elements in A, and then I have a set B. So let's say I have a bunch of elements in B. So let's say that in B, yeah, we have a bunch of elements and there's always arrows pointing at B, but let's say there's one element that is never used. Okay, so let's call this B1. Let's say B1 is never used. then that is our counterexample for onto function. So it says every output has at least one input. Well, B1 doesn't have an input, right? So in this case, we would say this is not onto. Right? This is not an onto function because you have an output there that is never used. So what does this look like? Well, this one's actually quite simple because this is saying for all B, right? So for all outputs, there's at least one input so that f of A is equal to B. So there's officially our definition of onto. Every B has at least one A so that f of A is equal to B. Now, you might look at these definitions, the one for one-to-one and the one for onto, and say they look they look very familiar because they look a lot like the definition for a function. In fact, they look like the part one and part two individually. And you're right, they actually do look like that, with the exception that the A's and B's are switched. So you can start to see that there is some relationship between the definition of a function and the definition of one-to-one and onto. We're going to get to that in 1 second. We're going to see what the relationship is, probably in the next video. But for now, just take this as the definition. And yes, they do look alike. So let's do a few examples here. So let's do the same one as we did in the previous slide. If we have f is a function that maps integers to integers, and we have this f is xy such that y is equal to x squared. I want to find out whether or not this is an onto function. So in order to answer that, we need to figure out, is it true that every single object in the output is used? Now, clearly here you can see, no, it's not. So even -1 is never used, right? So the negative numbers are never used. So what I can say is that this is not onto. And the reason is because -1 is not an output in f in this function. And that's good enough, right? So -1 is never used. So all I need to do is find one output, one element in B that is never used, that never acts as an output, and then we're done. All right. Now, in the same vein, we can actually say that 3 is never used, right? So the output 3 is never used. The output 5 is never used. The output 7 is never used, and so on, right? So in fact, only a very small amount of the inputs, or sorry, the outputs are actually used in this function. All right. So taking a look at the other function that we saw in the previous slide. So if we have integers to integers, and again, we have the relationship as xy such that y is equal to x plus 1. This time I want to figure out, is this is this an onto function? So in this case, we need to figure out, is there an output, right? Is there a y? Is there an output in the set B that is never used? Well, we can make an argument that no matter what y you give it, there's always going to be x minus 1, sorry, y minus 1, that is the input for that y, right? There's always a y minus 1 that acts as an input for that y. And every number, every integer has a minus 1. Okay, so we can argue that this is in fact onto because output y has input y minus 1. Okay, and that's it. That's all we really have to say. So we make a very quick argument that that yes, every output has to have an input that goes with it. So therefore, this must be an onto function. And this is kind of the thing that we're going to go through whenever you see a question like, is this function onto, is this function one-to-one? Probably the first thing you should do is try to find a counterexample, right? Is it possible that one of these outputs are never used? And if so, then you're done. But if it's not, it must be onto, it must be one-to-one, and therefore you have to argue that that whatever the the definition for those things are. Okay, now at this point, I want to point something out. We've already seen two examples. We've seen two examples of functions. So one that is like this, y is equal to x squared. So we saw that in that case, it is not onto, it is not one-to-one, right? So it's possible for a function to be not onto and not one-to-one. is it possible for a function to be one to one but not onto? And what about onto but not one to one? And the answer to both of those questions is yes, they can be one and not the other. And can they be both? Well, yes, because we saw another example of this, y is equal to x plus 1, which is onto, and also earlier we saw is one to one. So whenever you see a function that has both properties, one to one as well as onto, it is called a bijection. It is called a bijective function. It's also called a one-to-one correspondence. So you'll see it in some textbooks. It's called one-to-one correspondence. It's a function that is both one-to-one and onto. Now we saw one earlier, right? So the one, the y is equal to x plus 1. That function is an example of a one-to-one correspondence. But there's also another function called an identity function. So I want to share with you very quickly what an identity function looks like. So identity function usually is in the form of I of A, where A is just a set, and this maps set A to itself. So really what the identity function does is it maps each object or each element in A to itself. So let's say A is the set ABC. Then the identity function of A, of small a, is equal to A. Identity function of B is equal to small b, and identity function of C is equal to C. So I guess we can go further with this definition and say that the identity function of integers to integers is the relationship that y equals x. Right? So whatever x is, that maps to y. Right? So 1 goes to 1, 2 goes to 2, 3 goes to 3, and so on. So you might look at this and say, well, that's, is this even useful? Is this identity function actually useful? Well, it turns out that when we do a proof, it sometimes we can specify that a function is really nothing more than an identity function. And we're going to take a look at this a little bit later on, but just understand the notation here. Okay, so whenever we talk about I of A, identity of A, we're talking about a set A that maps objects to itself. Okay, the objects in A to itself. Now, the last thing I want to say about this is that if we have a function like the identity function here that maps, all the objects to itself, it is guaranteed to be a bijection. It's guaranteed to be a bijective function. It's both one-to-one and onto, right? So every element in the output is just the same as the input, right? So therefore, it's onto. Is it always one-to-one? Well, you only have one output, and for every output, you have one input associated with it, like itself. So therefore, it must be one-to-one as well. So the identity function is always a bijection. Okay, it's always a bijective function. All right. So the last thing I want to talk about in this subsection before I end off this video for today is just to do a few examples just to make sure that we understand the definitions of one-to-one and onto. And we're going to pick up from this point in our next video. So if I give you these functions, A, B, C, and D, I want to find out, are they one-to-one? Are they onto? It's just a simple yes or no question. All right, so I'm going to start at the bottom here. Okay, so you see how D has this kind of these arrows going on here, but hopefully you realize that D is actually not a function. Okay, so so the reason is because 1 is not going anywhere, right? So remember the definition of a function is that every input has exactly one output, right? Every input has exactly one output. So 1 doesn't go anywhere. So that's actually a counterexample right there. But the second problem is that you see 2 actually goes to A as well as C. Again, the input 2 actually has 2 outputs. So again, we can use that as a counterexample. It's not a function. So if it's not a function, is it one to one? Is it onto? And the answer is it's not applicable. Okay. So it's not that it's not one to one and not onto, it's just that there's no such definition. The definition is one to one function, an onto function, right? So if I have something that's not classified as a function, I can't call it one to one. I can't call it onto. There's nothing like that. Okay. So let's go back to A. Let's go back to function A. So just verify that the rest of the three, A, B, and C, are in fact functions because every input has one and only one output that is associated with it. And I want to figure out whether A is a one-to-one function. The answer there is no, because the definition of one-to-one is every output is used at most once. A is used twice. Okay, so it's not one-to-one, but it is onto because every output is used at least once. All right, what about function B? Function B is one-to-one because every one of those outputs are used at most once. Now you might be saying, wait a minute, A is not used. Is that okay? So the definition is that every output is used at most once. So 0 times is okay, right? So at most once. So yes, this is one-to-one, but it is not onto because once again, A is never used. So it's not true that every output is used at least once. Okay, so it's not onto. All right. What about C? Well, C, it is one-to-one. Every output is used at most once, and every output is used at least once. So C is actually a bijection. It's bijective function. All right. So we can make a few points from what we see here. And the first point I want to make is if you take a look at A with the sets that are set up the way they are. So we have the inputs 1, 2, 3, 4, and we have the outputs A, B, C. Is it possible to make a function out of those sets that are one to one? That is one to one, sorry. So uh, right here, we said this is not one to one. This function is not one to one. But can we make a one to one function? Well, if you think about it a little bit, the answer should be no. I can never make a one to one function out of those two sets. And the reason is, as soon as I try to delete one of the lines, right? So let's say I delete that arrow, it's no longer a function, right? So is it possible in this scenario, given 1, 2, 3, 4 as the inputs and ABC as the outputs, to make a one-to-one function? No, it's not possible, right? Because there's always going to be one output that is used at least twice. Okay, so just keep that in mind. When the size of A, now here we're talking about set A and set B, right? When the size of A is bigger than the size of B, then there cannot be, so there are no one-to-one functions. Okay, there can never be any one-to-one functions. Okay, now just take a second just to verify that. Okay, make sure you're okay with that point. But I'm going to make the same point for part B. For part B, I said here that this is not an onto function, but with the same sets, can I make an onto function? Well, again, it's no, because the most number of arrows that I can have in this case is 3. I can only have 3 arrows. There's always going to be one output that is missing, right? So here A was never used, but there's always going to be one output that is never used. So again, I make a very similar point. If the size of A is less than the size of B, right? So for this function, for a function A goes to B, right? If the size of A is less than the size of B, then there cannot be any onto functions. Now, these are very important points. So as we move on to the next video, I want you to keep this in mind, okay? So size of A is less than size of B means no one-to-one functions. Size of A less than size of B means no onto functions. Now, there is a contrapositive statement to what I've just created here. So if you remember, contrapositive is P implies Q, right? So the contrapositive, sorry, the contrapositive of P implies Q is not Q implies not P, right? So not Q implies not P. So if we take the contrapositive of the statement that I just wrote down, it means that when I have one-to-one functions, okay, so the opposite of no one-to-one functions, I do have a one-to-one function. When I have a one-to-one function, This implies that the size of A must be less than or equal to the size of B. You see, I just took the negation of both sides, right? So P implies Q, not Q implies not P, right? So when I do have a one-to-one function, this guarantees that the size of A is less than or equal to the size of B. So just keep that in mind because this is going to be very important to the next topic. Similarly, when I have an onto function, what can I say? When there's an onto function, the size of A must be greater than or equal to the size of B. All right, so I hope you were able to follow that last point. But the next point is what if I have a bijection? What if I have a function that is one to one and onto? So anytime we have a bijection, a bijective function, this means that both of the right hand sides are true. That means the size of A must be equal to the size of B. This is a guarantee. So when I tell you that there is a one-to-one and onto function, right, then you can guarantee that the size of the set A and B are the same. The domain and the codomain must be the same. The size of the domain and codomain must be the same. All right, so that's what I wanted to show you in this example. Um, there's one last thing that I want to talk about in terms of onto functions. So again, onto functions, the definition is that every output is used at least once. Right? Every output is used at least once in the function. But we had a special term in the last video about the outputs that are actually used in a function. We called it the range. So just take note of this, that whenever we say a function is an onto function, really what we're saying is that the range of that function is equal to the codomain. The range is equal to the codomain. That's another definition for an onto function. Okay, so keep that in mind because that's an alternate definition. But ultimately, onto function, every output is used at least once. One-to-one function, every output is used at most once. So keep those two things in mind. Okay, so I think that's all I wanted to cover in this video. So I will stop the video now and I will see you in the next one.